Okay, I wanted to start off by talking again about the example of the Crossflow hydroturbine analysis because it uses the control volume techniques that are the standard ways in which hydroturbines and wind turbines are analysed. And excuse me, I'm going to be using control volume techniques in this lecture to start with, and then again when we get on to wind energy. You don't need to be particularly familiar with them to understand what I'm doing, but if you look through the Crossflow turbine example, I think you'll be able to follow it reasonably well because it's fairly straightforward and it shows all the components of a control volume analysis that we need for this course. So I'll skip down to the picture or the image of the Crossflow turbine. This is the one that I ended the last lecture on. And I talked about the nozzle, which is, I can't use a laser pointer in PowerPoint, but you can probably follow the cursor as I follow the nozzle. The water comes in to the nozzle and the nozzle distributes it to the blades. And the blades are combined on a hydroturbine called a runner. That's the English term for it. The water then exits the turbine, and we've done a lot of computer models of these turbines, and the exit area, the exit flow, seems to always be very close to the inlet flow for reasons that we don't entirely understand. So what we need to do with the nozzle of the Crossflow turbine is to convert the available head into kinetic energy of the water that enters the turbine. And we're going to see in the next lecture that that's exactly the same principle that is used for the Pelton turbine. That the first stage of the energy extraction process from these turbines is to take the head, which is by and large the potential energy from the top of the water in, say, a dam and the turbine itself, convert that into kinetic energy in the nozzle, and then the job of the blades is to extract that energy and turn it into power. So when we apply control volume techniques to a turbine like this, we use the principles of conservation of mass, conservation of angular momentum, sometimes conservation of linear momentum, particularly if we're interested in the forces on the device. And when we get onto wind turbines, that we'll see that that's an important component of wind turbine analysis. But for hydro turbines, we're primarily interested in conservation of mass, conservation of angular momentum, and conservation of energy. The reason to be interested in conservation of angular momentum is that it is often easier to use that principle to determine the power that's extracted by the turbine. So if I'm going to use a conservation of angular momentum approach to this turbine, I would draw a control volume around the runner, and I would look at the angular momentum that is entering the runner through the nozzle or from the nozzle, and the angular momentum that is exiting the runner through the exit flow. And the difference between the angular momentum that's coming into the blades and the angular momentum leaving the blades is going to be the torque acting on the axis of rotation. And if we have a steady flow, and all the control volume analysis that we're going to be looking at assumes the flow is steady because that makes the analysis a lot easier, then as soon as we know the torque, we simply multiply it by the angular velocity of the blades, and that gives us the extracted power. And if you look down through here, the first two equations here use the principle of conservation of mass. So the mass flow rate in terms of cubic meters per second that is entering the nozzle through the throat has to be equal to the mass flow rate in cubic meters per second that is going into the runner, into the blades. Okay, and that's basically what that expression says. And that immediately gives us an expression for the radial velocity, because the radial velocity that is coming in to the runner through this point here is the means by which the water is actually entering the runner. In addition to the radial velocity, the water has a circumferential velocity. And that circumferential velocity gives it the angular momentum that we need to extract torque. So when we do a control volume analysis, we often have to distinguish between the velocity components that cross the boundary of our control volume, sorry about that, and the other velocities which are often associated with conservation of angular momentum. So these first two equations are immediate consequences of conservation of mass. And indeed, the next equation is as well, because to get equation 3, all we assume is that the radial velocity that is entering the runner of the turbine is constant across the entry. And if you think about it for a few moments, you need to have that condition on the entry flow because the blade geometry is fixed. And so if you have a fixed blade geometry encountering a varying flow, then it's likely to perform inefficiently. So we want to be able to determine the radial velocity entering the runner on the assumption that that radial velocity is constant over what is usually called the entry arc of the turbine. And if you make those assumptions, then you end up having designed the nozzle. What you see there is the equation for the shape of the nozzle. So we've done a major part of the design of this turbine simply by considering the conservation of mass of the flow in the nozzle. Then if we go down to equation 4, we see the principle that I've just enunciated or just stated. This is the energy that's available from the water. H is the head, the available head. G is the acceleration due to gravity. Qm is the volume flow rate, and rho is the density. Sorry, that says Q in. Yeah, I think, yeah, that's why I put it there. And so we want that amount of energy to be converted into kinetic energy of the flow entering the runner. And if we do that, we get equation 5, which is a consequence of conservation of energy. So I've used conservation of mass, conservation of energy. And then finally, what I do is use conservation of angular momentum. So you see in the angular momentum equation, u theta, which is the circumferential velocity, times the radius of the entry. So R1 times u theta is the angular momentum that is entering the control volume. And the amount of that angular momentum that is entering is the density times the volume flow rate. And therefore, we end up with an expression for the optimum operating condition, because we want the condition to be where the energy extracted by this is a torque. Sorry, I've used a different symbol I should have used a better symbol for torque. Multiply that by omega, and we have the power extracted as torque times omega. We balance that against the kinetic energy term, and we have a condition for maximizing the performance of this turbine. And in probably about the end of this lecture, we're going to see exactly the same way to optimize the performance of a Pelton turbine. Not only do we get that, but we get the angle of the streamlines coming in to the blades. And that is a very important piece of information, because the angle of the streamlines, if my pen is a streamline of the flow coming into the runner and my hand is one of the blades, then those angles have to be very closely the same. Okay, so what you can see on this page here is a very, very simple derivation of most of the important operating parameters for this turbine. The only thing that important thing that you don't get out of this analysis is what is the optimum number of blades to have in the runner. Okay, because this simple analysis is independent of the number of blades. To answer that question, you need to do very sophisticated computational fluid dynamics. It's a two-phase flow problem, and we've done quite a lot of that. Interestingly, the computational fluid dynamics analysis supports these results. Equations 1 and 2 are accurately reproduced in the CFD, and equation 7 underpredicts the optimum power by the optimum speed of the runner by about 5%. So it's remarkably close to a simple analysis. So if you haven't yet had a look through this example of the Crossflow turbine, please do it. And if there's anything in there that you don't understand, which is quite probable because I've gone through this in about 10 minutes, not very long time, please feel free to ask a question on it. And as I said, we're going to be using very similar principles to this in the lecture that I'm about to start now. So I'll stop sharing that screen. I'll open up my PowerPoint. So this is the PowerPoint that's labeled Lecture 2, which I've put up on Google Docs. So I'll share the screen again and go to Lecture 2.
Professor, can I ask a question about this?
My word.
So you used just the conservation of mass and angular momentum, but you also mentioned that we just can use also the integral form of Navier-Stokes equations to calculate the forces.
Yes.
So do you need that equation at all? Maybe you needed to optimize the shape of the particular blade?
Yes. You won't get a lot of information on blade shape from the simple analysis because it basically treats the blades as a black box. Okay, you're just interested in what's coming in and what's coming out. Okay, to do a thorough design of the turbine, to choose the number of blades, even if they're circular arc blades, you still have to choose their length and you have to choose their orientation. And the only way that you can do that in detail is computational fluid dynamics. And a number of years ago, I had a PhD student. This was his PhD project. And we showed how computational fluid dynamics could be used to design these turbines to have a very high efficiency. So yes, it's always an interesting question when you use very simple integral forms of the equations and finite control volumes. How far can you go with that sort of analysis? We'll see a similar thing with the Pelton turbine. And when we get on to wind turbines, we're going to spend a little bit of time looking at the Betz limit for the upper limit on wind turbine performance. And that's another example where you use a finite control volume and very simple forms of the integral equations. Okay, so here is Lecture 2, which is up on Google Docs. I'll turn the laser pointer on. And to start the lecture, so this is the first of the lectures specifically on hydroturbines, and I'm pointing out the 2021 hydropower status report from the International Hydropower Association. It doesn't have any information that is specifically relevant to the course, although it does talk about pump storage hydro. And pump storage hydro is one of the storage technologies that we're going to be looking at towards the end of the course. There is a little bit of information there on Russia. There's a section of that report that talks about the extra capacity that was installed in 2020. So Russia is high up in the world league states, as we knew, for hydropower, and is maintaining that by additional installations. And you can see the same is true for Canada as well. I think it's something like 60% of Canada's electricity comes from hydropower. I think it's the highest fraction in the world. I'm not sure what the numbers are for Russia. Okay, one of the interesting things about well, there's two very interesting things about hydropower. The first is that it's the oldest form of renewable energy. Okay, the first hydropower turbines at a large scale were installed about 130 years ago. And that history has an impact on how the technology has developed. And I'll be talking a little bit about that, mainly in terms of the issue of how do you connect a generator to a hydroturbine to get the power out and fed into the grid. The other interesting thing about hydropower is that there's a very wide range of turbine technology. We've seen the Crossflow turbine. Here is 3 types of turbines, and we're going to be looking at the Pelton turbine, which is a different technology again. What is usually the case with the hydroturbine is that the water comes in radially. And what is called a wicket gate or a stay vane sometimes is a device whose job it is to adjust the angle of the flow coming into the turbine. The reason for that we'll look at later. Then the way in which the water interacts with the blades tells us what type of turbine it is. If the water goes past the blades primarily in the radial direction, we call it a radial turbine, radial after radius. If the flow direction changes substantially as we go through the turbine, that is a mixed flow turbine. If the flow is primarily in the parallel to the axis of rotation, we have an axial flow. We have, in this case, a turbine that looks a lot like a ship propeller, or indeed a little bit like a wind turbine. So they're the 3 basic distinctions between turbine type. If we're going to analyze any one of those turbines, a possible control volume I've drawn in the bottom of the slide there. So what you would do would be to look at the mass coming into the control volume, the mass coming out of the control volume, the angular momentum coming in, the angular momentum coming out, and say the energy coming in and out. Okay, these few lectures or these few slides are really about the context of a turbine. So whatever type of turbine we have, this diagram shows a very typical and simplified installation of that turbine. If we look at what happens between point A and point B, then there's basically 3 ways in which the energy content of the water can change from A to B. And for the moment, we're not looking at energy being extracted by the turbine. That comes in a little bit later on. There can be a potential energy change. If the elevation of A is considerably higher than the elevation of B, then there's a significant potential energy in the water. And most of the turbine types that we're going to be looking at rely on a head difference between A and B. Okay, that head difference can be very large. I have a friend in Calgary who owns a company that installs hydroturbines, and the biggest head difference in a turbine system that they installed was 4 kilometres, 4,000 metres. Okay, it can be substantial. There can also be a kinetic energy change. There can also be a pressure change. And counteracting those sources of energy, if you have any pipe work between point A and point B, and that pipe work can include valves to shut the flow off and things like that, there are going to be frictional losses in the pipe work. And usually when we look at the energy that is available for a hydroturbine, we have to subtract the losses that occur in the pipework. And I'll give you some simple examples of how those loss calculations are done. Okay, so this is the same diagram, but it's got a little bit of extra information on it. And that extra information is that if we start at the water surface behind the dam and finish at the water surface after the dam, then normally we assume that the velocities at those points are equal, and that also equal to zero. So basically, there's no kinetic energy change between A and B. Also, too, we have atmospheric pressure acting on A and B, and the atmosphere has a variation of pressure with density and height, exactly the same equation as applies to water, but the density of air is about 800 times less than the density of water. So the air pressure difference between A and B is normally zero or negligible. Okay. So of the terms in the head equation at the top, the two middle ones drop out in most cases, or they're so small that we neglect them. And so that means that the energy that is available to that turbine is due to the difference between the physical head and the losses that occur in the pipework. And that's the statement that is behind the next statement that people often make. Most hydro turbines are head-driven. They are driven by their head, which represents the available potential energy. For some reason, hydropower always works with potential energy in meters rather than in units of G times H, which is the proper energy term per unit mass. Okay, the loss calculations can be quite complex, but the basis of them, and remember what I said before, hydropower is a very old renewable energy technology. So people had to be able to design hydro turbines long before we had big enough computers to do computational fluid dynamic simulations of all the important components of it. The easiest way to accommodate the loss is through what's called a friction factor, this F that appears here. And its relationship to the losses, provided those losses are due entirely to friction, depends on the velocity in the pipe, the length of the pipe, and the pipe diameter. And if we use the relationship between the velocity and the flow rate, that if we're interested in the average velocity, then the average velocity times the flow area in the pipe is equal to the volume flow rate, then we get a very simple expression for the total head that's available to the turbine. It is simply, again, the difference in elevation minus the friction losses. And so basically we can get an expression for the available head, provided we know what the friction losses are. And if you look at a textbook on hydropower, you will see a lot of, there's probably a separate chapter in that book that talks about how you calculate those losses. In the old days, that meant having charts of friction factors where you would, depending on the appropriate parameters, you would be able to get the friction factor. A very simple expression for it is shown in this slide here. There are many, many expressions for little f. This is just a simple one that I happened to come across a number of years ago when I was starting to write these notes. And it conveys the basic features of the frictional losses in the pipe. And remember, these frictional losses are due to friction at the wall of the pipe. Okay, the frictional stress that is transmitted from the fluid to the wall is due to the velocity gradient at the wall times the friction, times the viscosity of the fluid. And so what that means is that a friction factor has to account for the roughness of the pipe. So this epsilon in English is a measure of the pipe roughness. D is the pipe diameter. And this is a purely empirical equation. In other words, it's an equation that has been developed over many years with practical experience for checking out how these equations work. And that equation is good enough to show the basic features of the friction that we need. One important one of those is that for a given roughness, the friction decreases with increasing diameter. Okay. Sorry, have I got that round the wrong way? I better pause on that and check it later. I meant to check that before I started, but I'll come back to it later. Okay, here's an example. So we have point A at an elevation of 915 meters. We have a length of 350 meters of pipe, a pipe diameter of 300 millimeters, and a roughness of 0.046 millimeters. These are very typical numbers, and this value of the friction factor, 0.013, is a very typical value of the friction factor. And the point about doing these examples is just to give you a sense of the significance or the importance of pipe friction in these calculations. So if we do that, so I meant to say before that the head difference, I forgot to mention that the lower reservoir was at 892 meters. The difference in physical head is, what's that, 15 plus 8, 23 meters. And the actual available head is about 13 meters. This is a smaller proportion of the physical head difference that you get in most calculations. Okay, typically the friction losses will be less than about 10% of the actual elevation difference. And having found the head, all we need to know then is the flow rate in cubic meters per second and the efficiency of the turbine. Because what we see here is the basic turbine equation that relates the power produced according to the efficiency, the acceleration due to gravity because of the height change being converted into potential energy, and the mass flow rate, which is the density times the volume flow rate. And we just plug the numbers in and get the power output. So I've got a few very simple calculations of turbine performance based on these simple equations, basically just to give you some sense of how important the frictional losses are, and also too what are sort of typical performance of these sorts of turbines. Okay, I mentioned before that there's a wide range of hydroturbines that are available, and that the range that is available is often put on a chart where the vertical axis is the available head and the horizontal axis is the volume flow rate Q. Okay, because it is the product of those two that gives the available power for the turbine. And if you look on this chart here, you'll see not every type of turbine that's available, but representative turbines. So, for example, the Crossflow turbine that we analysed before is typically a fairly low flow rate and a fairly low head. If we want very high heads, then remember I was talking about heads that were comparable to 2,000 metres. That is a regime of Pelton turbines. When we come down in head again, we get into the area where Kaplan turbines are important. And a Kaplan turbine looks like a ship's propeller. It is an axial flow hydro turbine that is very similar to a horizontal axis wind turbine. The biggest region of all is the Francis turbine. And I'll explain a little bit more what a Francis turbine looks like later in the class, because it's not easy to explain it simply. Francis turbine is probably the most common of the large turbines, and it is the turbines that Ivan and Rustam's colleagues in Novosibirsk have done a lot of work in studying the performance of. The advantage of a chart like this is that it can give you a very easy way of knowing what you should be looking for if you have a turbine project. Because if you are setting up a turbine project, then the resource assessment that you would do would identify the head that's available and would identify the flow rate that's available. Identifying the flow rate is usually much harder than identifying the head, and I'll tell you a little bit about how that's done towards the end of the hydroturbine lectures. You can see coming down at an angle, typical power outputs of these turbines. So the biggest Francis turbines are in fact very large. Okay. The Three Gorges Dam project in China, I'll show you some further information on that later, which is the biggest hydropower project in the world that uses Francis turbines. I don't know whether you know about the Ethiopian project to dam the Blue Nile, the Grand Renaissance dam that the Ethiopians call it, which is going to produce 6,000 megawatts of power when it's finished. That is going to be all Francis turbines. You'll see if you open up any book on hydroturbines, you'll probably see a chart like this. You'll see different types of turbines on the chart, and you'll probably see different areas where the particular turbine type lies. This is really just meant to be an indicative chart. It's not a chart that you would say, okay, I have a flow rate of 20 cubic meters per second and a head of 100 meters. I must have a Francis turbine. What it's really telling you is that you probably should look at a Francis turbine for that site, but possibly also a Kaplan turbine as well. Okay, so we're going to move on to another turbine type, the Pelton turbine, which is actually closest in method of performance to the Crossflow turbine than any of the other ones that we have looked at in the meantime. This shows the runner of a Pelton turbine, and there's one of the workers who helped to build it, just to give you a sense of the size of it. And if these things look a little bit like buckets, that's exactly what they're called. Each of those is a bucket for this Pelton turbine. And one of the the first fascinating thing about Pelton turbines is how fundamentally simple they are. All that happens in a Pelton turbine is a jet of water is aimed at those buckets to force the buckets to rotate, and that produces power. The other amazing thing about the Pelton turbine is that it can do that with a high efficiency. It's relatively easy to get efficiency well over 90% with a Pelton turbine. And in fact, the main cause of inefficiency in most Pelton turbines is the air resistance of the runner, the drag on the runner as it rotates through the air. And I'll show you an example of that later on. Okay, so now we're looking down on a typical Pelton turbine installation. So here in red, I've identified the runner, which is what we saw in the previous diagram. And you can see around the periphery of the runner are 6 nozzles. And the purpose of those nozzles is to simply aim a jet of water at the runner to make it rotate. As I said, an incredibly simple design, and I'm continually amazed just how efficient a Pelton turbine can be with that very simplistic design. Okay, so typically when you do the analysis, you make a number of simplifications. And here we're looking at some of them. We have a jet of water that is aimed at the runner of the turbines and is hitting bucket number N at this point here. The the buckets and the turbine are rotating at an angular velocity of omega meters per second. And as we will see, this nozzle is designed when it's producing maximum power to have converted all the available head for this turbine into kinetic energy. So the principle of design for the nozzle of a Pelton turbine is precisely the same as the principle of design for the Crossflow turbine that I started the lecture off with. So this jet of water is aimed at the buckets, and you can see around this point here is the splitter, as it's called, of the bucket. Now you begin to see why the buckets have the shape that they do. Okay, because the water comes into the buckets, is turned by the buckets, and exits at an angle of beta to the direction of the jet. And this angle beta, surprisingly, is usually close to 180 degrees. It's minimized in this figure here just to keep the arrows away from each other. So I forgot to actually put it on the slide that's coming up, but usually when you do the analysis of a Pelton turbine, you assume that beta is going to be 180 degrees. Okay, so I meant to also point out, you can see the splitter ridge in this photograph here, and now you can imagine the jet of water bifurcating along that splitter ridge, so half of it goes into the upper half of the bucket and the bottom half into the bottom half of the bucket. Okay, if we look at the way the buckets perform, then what we have to do from the basic control volume analysis, as we did for the Crossflow turbine, is to account for the angular momentum coming in to the control volume and the angular momentum coming out. So this is actually a slice horizontally through the buckets in the photo that you saw before. Sorry, vertically through the buckets in the photo that you saw before. So here's the splitter ridge here. Here is the velocity coming in, and here is the velocity coming out. If you read textbooks on hydro turbines, you will see that most of the analysis is done in terms of often very complicated velocity diagrams. It's possible to draw, for most types of hydro turbines and also gas turbines, very complicated velocity diagrams, and there's a whole range of different subscripts and names for the velocity components. I'm not really going to use any of that for this fairly straightforward explanation. I put this here largely in case you go to a textbook and are confronted with those velocity diagrams. What I'm going to do is give you the equations first of all, and then explain how they arise. So what we're going to do for this analysis is use only one of the conservation equations, the conservation of angular momentum. So what we're going to say is that the torque acting on the axis of rotation of a Pelton turbine is the mass flow rate, density times mass flow rate, which is given the symbol of m dot. So m dot is equal to rho times q. And I apologize, I didn't put that piece of information on the slide. I'll have to amend that. And that is multiplied by the difference between the angular momentum coming into the control volume and the angular momentum leaving. And I'm going to show you on the next slide that the difference in the angular momentum is the difference between the water jet velocity and the circumferential velocity of the splitter times the radius r. And there's a factor 1 minus cos beta 2 because the factors in this term here give the direction of the velocity that's coming into with the +1 or out of the control volume. And as we go down through here, I will assume beta 2 has a value of pi or 180 degrees. So I'm going to explain where this velocity comes from in the next lecture. But if you can accept what I forgot to put on the notes, that the mass flow rate is the density rho times the volume flow rate Q. This is the expression for the torque that is generated about the axis of rotation. If the angular velocity is omega, then I've got the power extracted. And what I can do then is look at the operating conditions that give me maximum power. Because one of the themes that covers all the technologies that we're going to be looking at in this course is the question, how can I get the most power out of my renewable energy technology? And we will see that for hydroturbines, wind turbines, and photovoltaics, that there are different strategies that are needed to achieve that. So if we've got a nice simple expression for the power output as a function of omega, then we recognize that omega is the only operational parameter in this equation that can vary. So if we're looking for a condition that gives us a maximum power, it makes sense to differentiate this expression with respect to omega. Set that equal to 0, and in one line, you have the condition that gives you optimum power is that the rate of rotation is equal to the jet velocity over 2 times r. Or alternatively, the jet velocity is twice the circumferential velocity of the turbine. And if you look at that in terms of the maximum power, assuming again that beta 2 is 180 degrees, then we get this expression here, which I've left a factor of 2 off. This should actually be divided by 2. I apologise for that. I'll put a corrected version of this slide up when I load the slides for the next set of lectures. So what that means is that the maximum power that we get out of a Pelton turbine occurs when we have the product of the mass flow rate times the kinetic energy coming out of the jet. So the jet design is equally important to the runner design. Okay, the jet has to be designed to extract the maximum energy or convert the available head into kinetic energy. And then the Pelton turbine itself has to be designed and operated in such a way that that converts all that available energy into extracted energy. Okay, where does that equation come from? Here's a very simplified explanation. What you see here is a red circle, which would be my control volume that I would draw surrounding the runner of the Pelton turbine. Now, one thing that I haven't said about control volumes is that it is usually easier to have an inertial control volume. In other words, a control volume that does not rotate with the turbine. The reason is very simple. If you have the control volume rotating with the turbine, you may have non-inertial effects like centrifugal and Coriolis forces. So it's usually easier to draw a stationary control volume around a rotating turbine. That's what I did. I didn't say it when I was explaining the Crossflow example. That's what I did with Crossflow. So if I have a stationary control volume, the jet is coming at velocity Vj, and just imagine that's an idealized blade. It's just a straight blade because that straight blade can be imagined to be accepting a velocity Vj minus omega r hitting it, and then a velocity omega r minus Vj leaving it. And so that means that if I transfer from the rotating blade back to the stationary coordinate system, then I get the expression that appears on the previous page, because V2 will be 2 omega r when I add on the omega r for the blade rotation minus Vj. So that explains where the velocity equation comes from in the torque equation here. Okay, how do we turn that into an example. What we're doing now is applying our expression for the available energy between the water surface and the exit of the nozzle. We're not doing it at the end of the turbine, we're doing it at the nozzle. If that is the case, then this term again will be equal to zero. We will still have loss terms. VA we can assume equal to zero, but now VB will be the velocity of the water at exit from the jet. And so what that tells us is that the best design that we can have for the jet is when the jet velocity is converting all the available head minus the losses into kinetic energy. And the loss equation that I've got here is a slightly more complicated version of the loss equation that I had before, because I have added an additional term that includes losses in bends and things like that. And so here's a simple example where we put that into practice. If you go through the numbers that I have provided, you get a very similar value of the friction factor that I had before. And then you can work out the volume flow rate, the jet velocity, the maximum power, and the operational speed that power is achieved at. So again, they're not difficult calculations at all, but these are the sort of very basic calculations that go behind, say, the feasibility study that you would do if you were going to do a Pelton Turbine project. Okay, so that's the end of the first part of the lecture on Pelton Turbines. It's about 25 past the hour by my clock, so I will finish there and go on to lecture 3, which is posted on Google Docs tomorrow. Yes, tomorrow. And I will add the extra information that I had left out of the slide on the Pelton example before then. Okay, does anybody have any questions that they would like to raise or comments to put into the chat?
I have one question.
Yep.
Cross turbine. You say that it is a multi-phase flow, right? In your CFD calculation. So my question: it is do a cavitation or do a free surface and bubbles inside of water? And the main question: what influence of this multi-phase you could see on your energetic characteristics? You mean that it's the best? So your easy calculation for how to choose a nozzle shape, is it influence of this multi-phase flow on this estimations?
Yeah, two very good questions. Can I separate them into the question on multi-phase and the question on cavitation? The multi-phase, okay. When you do research, you often do things because you anticipate what the referees who are reviewing your paper are going to say about it. And the main reason that we did the analysis using multi-phase models, and if people are not familiar with what we mean by that, a multi-phase model for a turbine would include the water that is coming in at the inlet there, and also the air that is entrained into the water flow as it goes through the runner and exiting the runner. So in principle, there will be, entrainment of air into the water as it goes through the runner. What we found was that was negligible. In other words, if we did the analysis or the simulation of a turbine with multi-phase flow and without multi-phase flow, we got virtually the same answers. Okay. However, we kept with the multi-phase model because we anticipated that when we wrote this work up and submitted it to a journal for publication, that's the sort of comment that a referee would make. Why didn't you use a multi-phase flow model for this? So that was the main reason that we do. It would probably have been a good thing to do, at least in one case anyway, to compare with not using a multi-phase or using a single-phase model. But I guess the thing then is if you've gone to the trouble of learning how to do multi-phase flow simulations, you might as well keep going. Now, the issue of cavitation is a very important one, and one that I hadn't planned to talk about in this introductory lectures because I thought I would be overloading people with concepts. But anyway, it is very important, and for many types of turbines. Interestingly enough, for the Crossflow turbine, we never found any cavitation in the inlet flow, in the first, what we call the first stage. The cavitation that occurred was always at the entry to the exit flow. And interestingly enough, it always occurred around the point of maximum efficiency. So we actually got quite a nasty shock when we went through the whole process of doing a lot of CFD simulations with varying numbers of blades, et cetera, to try and push the efficiency high into the 90s. And then we found that our most efficient turbines were cavitating. And cavitation occurs when the local pressure in a water flow is less than the vapor pressure. And what that means is that you effectively get bubbles formed in the flow. And those bubbles, they can cause noise, they can cause vibration, and they can damage the blades. And a lot of the off-design performance of turbines like Francis turbines is really about issues associated with cavitation. And yes, I think the same thing is likely to be the case with Crossflow turbines. Unfortunately, the computational work was actually meant to be the first stage of a two-stage project. And the second stage of the project was to use what we had discovered computationally to design and build a turbine to test in the hydraulics lab at the university. And we got to the stage of having assembled the turbine almost, and the hydraulics lab was shut down for at least 2 years. And then it turned out that the civil engineering department who ran the hydraulics lab decided that they didn't need a hydraulics lab, so we lost it completely. So we didn't actually get to I had a PhD student who was actually building a model Crossflow turbine with plexiglass nozzles, so we could put laser Doppler anemometers into it. And we were going to do a lot of detailed experiments, but we just got hijacked. So the upshot of all that is that I'm not sure what the real consequences of cavitation are for Crossflow turbines, and I don't think anybody really does. Sorry for a long answer. Do we have any other questions?
I also have another question.
Okay.
About chart when we have head and flow rate. You find different types of turbines. So and that big area of intersection of different types of turbines. And I want to ask what you guess. What type of turbine customers could choose if most type of turbine are suitable for this head and flow rate?
A really.
I mean,
yeah.
I mean, it's a really middle of this chart. The Kaplan, Francis, and Crossflows are suitable.
Yes, I mean, if I was drawing this chart, I would actually move the Crossflow down to the bottom left-hand corner. I think a power output of around 2 megawatts is probably far too high for a Crossflow turbine, although there is a company in Germany called Osberger who have just built a 3 megawatt Crossflow turbine. So it is possible to build them at high power, but I think they need an unusual combination of head and flow rate to achieve that. So I would actually move the Crossflow region down to the left, as I said, which gets rid of one of the turbines that I have to consider.
Yeah.
My understanding, and this is really stretching my knowledge of the practical applications of it, I think generally speaking that the Francis is preferred partly because you have a higher level of control over its operating conditions. Because a Francis turbine has inlet guide vanes, so you can do a lot of mechanical control as well as speed control. We're going to be talking in the next lecture about how you control turbine operations, what it means to control turbine operations, what conditions that you do it under. So I suspect the answer is probably something like that, but I don't. I'll ask my friend, the installer of hydro projects, what he would answer. That would be interesting to hear. But like I said when I was talking about this earlier, I think this has to be looked at as a sort of an indicator rather than this telling you exactly which turbine you would use for whatever combination of flow rate and head.
Okay, thanks.
Okay, I think I'll stop sharing again. No, there's nothing in the chat, so I think we're finished for today. So, see everyone except Ivani. Can you stay for a little while? I'll see everyone tomorrow.
Thank you. Bye-bye.
Bye.